In this video, we're going to explore two different special right triangles. The first is the 45-45-90 right triangle. So what does that mean? Okay, the 45-45-90, well, first of all, the 90 is this right angle right here. And here's what I'm saying. I am saying that this is an isosceles right triangle. How do I know it's isosceles? Well, I put tick marks on each side. Okay, this specific one has a length, this side has a length of 1, this side has a length of 1, meaning these two sides are congruent. If these two sides are congruent, then these two angles are congruent as well. Since the three angles in a triangle have to add to 180 degrees, okay, we know this one's 90, that means there's 90 left split equally. These are 45 and 45 degrees. Okay, great. So now we understand that this is a right isosceles triangle. Let's go ahead and explore the relationship between the three sides. These two sides obviously have to be congruent. If this has a measure of 1, this has a measure of 1. But how do these two sides connect to the hypotenuse? Okay, so go ahead and look what I've done. I've used the Pythagorean theorem. I said a squared plus b squared equals c squared. So x is my hypotenuse, it's my side c. 1 squared plus 1 squared equals x squared. 1 squared is 1, so 1 plus 1 gave me 2. Square rooting both sides. I've got x to be plus or minus the square root of 2. Now that's really good algebra, but in geometry, it doesn't make sense for the side of a triangle to be a negative value. So we drop the plus or minus and we just say that the answer is the square root of 2. Now this may not have any meaning to you. Okay, my leg is 1, my other leg is 1, and my hypotenuse is the square root of 2. You're probably not seeing any sort of a pattern. So let's look at another one. Okay, so this time I let each leg be 2. And again, I know I put this up here pretty quickly and you might need to pause for a second and process it. But if this leg is 2 and this leg is 2, the Pythagorean theorem tells me that the hypotenuse is the square root of 8. Okay, breaking that down using good algebra 1, I get the value of x to be 2 root 2. So 2, 2, 2 root 2. Maybe you're still not seeing the pattern. Let's do another one. Okay, so let's see if you can see a pattern now. If this side is 3 and this side is 3, look at what my Pythagorean theorem just got me. The hypotenuse is now 3 root 2. Okay, so how's this for a visual? On the first example I gave you, each leg was 1, and the hypotenuse came out to a root 2. But for fun I put the 1 in front of it, and I think you'll see why in a minute. So our second example, this side was 2, this side was 2, and the hypotenuse came out to 2 root 2. And the third example, this leg was 3, this leg was 3, and this was 3 root 2. So look at the pattern here. Okay, 1, 1, 1 root 2, 2, 2, 2 root 2, 3, 3, 3 root 2. Now do you see it? So let's go ahead and test your theory out. If the first leg has a measure of 15 and the second leg has a measure of 15, so this side's 15 and this side's 15, what should the hypotenuse be? If you guessed 15 root 2, you're right, and you see the pattern. So what does this pattern tell me about the triangles? Okay, this pattern tells me that the hypotenuse is always root 2 times bigger than the leg. If you put this in your calculator, this decimal will be about a 1.4. That's bigger than 1. So the hypotenuse is bigger than the leg, which we know it's the biggest side in the triangle, and specifically, this side will always be root 2 times bigger than this side. This is root 2 times bigger than this side, root 2 times bigger than this side, and root 2 times bigger than this side. So that's what the pattern's telling me. Now, how can I use this? So now I can give you a problem like this. Here's the actual directions. Find the missing side lengths in the given triangle. So look at the triangle. It is a 45, 45, 90. I'm giving you that this side right here has a measure of 37. So if that's 37, we know that this side must also be 37. And if those two are both 37, we know that the hypotenuse has to be 37 root 2. Easy enough. Okay, so what if I kind of go backwards here and give you the length of the hypotenuse? If I tell you that the hypotenuse is 74 root 2, can you find the measure of the legs? Well, sure. We know that the hypotenuse is longer than the legs. Longer by how much? By a factor of root 2. So if I divide out the root 2, I know that this side has to be 74, and then this side must match and also be 74. Not so bad. All right, ready for a little harder one. So take a look at this picture. What if this side length is 19 root 2? That's a leg. We're used to seeing the root 2 in the hypotenuse. So what do I do now? Well, first, I know that whatever this leg is, this leg must be the same. It is an isosceles triangle. So if this is 19 root 2, this is 19 root 2. Now, what about the hypotenuse? The hypotenuse has to be longer. So if you think that this side, the hypotenuse, now is going to be 19, really, you got to rethink that. Okay, I'm telling you, it can't be 19, because how can the hypotenuse be smaller than the leg? And the answer is, we of course know it can't be. Okay, so how are we going to find this hypotenuse? If you've been listening to the wording I've been using, I keep saying that this side, the hypotenuse, is longer by a factor of root 2. So that means when I'm going from a small side to the bigger side, I need to multiply. Multiply by what? Multiply by root 2. Okay, so look at the math. 19 root 2 times root 2. Well, here's the 19. The square root of 2 times the square root of 2 is 2. So 19 times 2 gets me 38. That means the length of my hypotenuse is now 38. Okay, so let's go ahead and tackle this case. I can tell you up front right now that this is the hardest case you will deal with in a 45, 45, 90 triangle. Okay, there's two ways to go about this. So I could, in fact, go ahead and put an X here and put an X here and do some Pythagorean theorem. Okay, that's a valid option, but it's not the option that I'm hoping for. I'm hoping for something a little bit better and more direct, because I kind of have an idea now of the relationship between these sides. I know that this is the biggest side in the triangle, and it's not just randomly bigger than this side. It is exactly root 2 times bigger than this side. So if I'm going from the smaller side to the bigger side, I needed to multiply by root 2. But when I go from the bigger side to the smaller side, I'm going to divide by root 2. Okay, it's really easy when this side had a root 2 in it to just drop the root 2. But how do I divide 30 by root 2? Okay, so first make sure you really understand why are we dividing? Because we're going from a bigger side to a smaller side, and that's how the relationships here among the sides work. Smaller to bigger side, we multiply to get bigger. We divide to get smaller. I know this is the biggest side, therefore I have to divide, and the factor I divide by is root 2. So now we understand the geometry of what we need to do. But let's talk about the algebra 1 here. I can't leave my answer with a square root in the denominator. So the way I get rid of the square root in the denominator is I have to rationalize the denominator. So going back to algebra 1, we know that to rationalize the denominator on this fraction, I need to multiply by root 2 over root 2. Okay, remember, the equivalent of this is 1. So I'm not changing its value, I'm just changing the form in which it's written. So multiplying across, on top I get 30 root 2, and the square root of 2 times the square root of 2, the square root of 2 times the square root of 2 is 2. And then last but not least, we can go ahead and reduce the 30 and the 2, which is how I'm getting a final answer of 15 root 2. So that means that this side is 15 root 2, and this side is also 15 root 2. And we're done. Okay, quickly, on a little side note here, if you don't understand this idea of rationalizing the denominator, I did make a previous video on that. So look in the Algebra 1 folder on radicals. Okay, again, this is the hardest case scenario. Why? This part shouldn't be hard to understand. It is all of this that generally holds kids up. So just remember, to go from here to here, we multiply. To go from here to here, we divide. It's that simple. All right, so 10 minutes into this video, I bet you're probably ready for this video to be done. However, we've only covered the 45, 45, 90 triangle. There's a second special right triangle that's the 30, 60, 90. So look at the equilateral triangle I've drawn here for you. Okay, obviously an equilateral triangle with each angle of 60, that's not a 30, 60, 90. But let me show you where the 30, 60, 90 comes from. Okay, so if I drop this altitude right there from any of the angles, but I'm going to choose the top angle in the 60 degree, I drop an altitude, there's my 90 degrees. There's my 60 degrees, so I've got this one taken care of and this one taken care of. But where am I getting the 30? Well, look what happens up here with this 60 degree angle. As soon as I drop the altitude, it is going to bisect that top angle. Okay, so my top angle is now split in half. The 60 degrees that we used to see becomes now 30 and 30. So if I look at just half of this triangle, so let's go ahead and highlight that so you can see it. Okay, so take a look at our picture. And now we're going to really focus our attention on this half of the equilateral triangle. Okay, so here's my 30, here's my 60, here's my 90, and we need to talk about the relationship between the side across from the 30, which is there, across from the 60, which is there, and across from the 90, which is there. Okay, so let's say each side of my equilateral triangle has a length of 10. Well, remember, we're not really interested in this half of the triangle over there. So special property for my equilateral triangle says that when I drop this altitude is also a median. So what does that mean? That means that this segment that I just dropped down, this altitude, also is going to bisect the side to which it is drawn. In other words, it's going to take that 10 and cut that 10 in half and put 5 to that side and 5 to that side. Okay, so quickly, just make sure you see, yes, this side length is still 10, but now the 10 gets split into 5 and 5. So just like it bisected the angle up top and gave me 30 and 30, it bisects the side. Well, why is that important? That's important because now look at, I've got two sides on my 30, 60, 90 triangle here. So the side across from the 30 is 5, and the side across from the 90 is 10. Hold on to that for a second. So what happens if I change all those 10s to 4s? This side's 4, this side's 4, this side's 4. The altitude / median divides this side into 2 and 2. Okay, great. But look at, across from my 30 is 2, across from my 90 is 4. Are you seeing that pattern yet? Are you seeing the relationship between these two sides? I think you should be able to follow me when I say that this side across from the 30, so just from here to here, that is always going to be half of this side. Because how did we get the 2 to begin with? We took the side length 4 on this side, and we cut the 4 in half, which gave me 2 and 2. So across from the 30 always must be half of what's across from the 90. Okay, well, what about this side now? So setting this side equal to x, and again, I'm looking at just this triangle here, okay? I did a little bit of Pythagorean theorem, so a squared plus b squared equals c squared, and follow my algebra 1 here, where I've got x is the square root of 12, which simplifies to x is equal to 2 root 3. So I bet you don't see a pattern between 2, 2 root 3, and 4. I wouldn't see a pattern if that was all that I was presented with. So let's go back to our previous example, and maybe then you'll see the pattern. Okay, again with the Pythagorean theorem. This time my a squared was 5 and my c squared was 10. So a squared plus b squared equals c squared. X squared came out to 75, square root both sides. The square root of 75 breaks down to 5 root 3. Do you see the pattern, or do you want to see it in the table format? So in order to make room for the table, I took away the other half of the equilateral triangle. So remember, this is just half of that equilateral triangle, which is where the 30 comes from, and so on and so on. So my hypotenuse, we started by saying let each side on the equilateral triangle, well, let each side be 4, or let each side be 10. And what we found is the side across from the 30 always ended up being half of these numbers. So half of 4 is 2, and half of 10 is 5. Well, how did we get these numbers? This was, remember, Pythagorean theorem. So now let's look and see if you see a pattern. We went 4 to 2 to 2 root 3, 10 to 5 to 5 root 3. Do you see it yet? So what if this side was 16? Okay, if this side was 16, then all the sides would be 16. So when I drop the altitude, this half becomes 8. But what about the side across from the 60? What does the altitude length become? If you see the pattern, then you'll easily know that this piece, or this piece right here, should be 8 root 3. So again, I ask you, well, what is the pattern? What you should see is the hypotenuse gets cut in half to make the side across from the 30. Yes, obviously, we knew that. But how do I get this dimension, or this side length? I take this side and I multiply it by root 3. So really, this, I'm telling you, is the most important side in the triangle. Because once you know this, you multiply it by 2 to get the hypotenuse, or by root 3 to get the altitude. So let's say it again. Once I have the 5, I multiply it by 2 to get the 10, or I multiply it by root 3 to get the side across from the 60. So if I know the 8, I multiply it by 2 to get the hypotenuse, and I multiply it by root 3 to get the side across from the 60. Think you've got it? Okay, so easiest case first. Ready? Here we go. I'm telling you that the length of the hypotenuse is 48. This is a 30, 60, 90 triangle as marked, so let's find the missing side lengths. So what do we know? You have to envision the other part of the triangle over there. If each side is 48, then I know this half has to be 24. Okay, so if this side's 24, I don't want to do Pythagorean theorem. I could, but I don't want to. What's the shortcut? What's the fastest way? The fastest way is to realize that this side needs to multiply by root 3 to become that side. So that means that across from, here's my 60, across from my 60 must now be 24 root 3. And there's my pattern. Across from the 30 is half of what's across from the 90, so this is a 1 to 2 ratio. And then across from the 60 is root 3 times bigger than what's across from the 30. So here to here, this is a 1 to root 3 ratio. All right, seems easy enough. Let's do another one. What if this time I'm given the side across from the 30 as 17? Well, now how do I figure this out? Okay, here's what I know. I know that across from the 30, that is half of the full side. So 17 times 2 gets me a side length of 34, and therefore my hypotenuse must also be 34. Okay, so how do I find this side? Well, remember, across from the 60, this side is root 3 times bigger than 17. So that makes this side 17 root 3, and I'm done. So most people will think, when I give you the side across from the 60, this is your hardest case scenario. And that may in fact be true, but not this example. Because in this example, I can see the root 3. Okay, I know that when I go from the side across from the 30 to the side across from the 60, normally I multiply by root 3. But now I'm going from a bigger side to a smaller side. So I have to divide by root 3. Since the root 3 is already there, when I divide it out, this side just becomes 22. Okay, that's not so bad. I see it. From the 22, I multiply and get the root 3, or from the 22 root 3, I divide to get the 22. And if this is 22, that's half of the full side, remember? So now that makes my hypotenuse 44. I told you this one wasn't so bad. Okay, so this is the one you've been waiting for. This is the one that is your hardest case scenario. And not because the math is crazy complicated to understand, it's because of the Algebra 1 that's required to complete the problem, right? This is the same mindset as the last problem. When I know it's across from the 60, I divide it by root 3 to get the side across from the 30. But unfortunately, I can't leave this side written in this form. So across from the 30, yeah, that's the right math to take it and divide it by root 3, but I have to rationalize it. Okay, so some good Algebra 1 to rationalize, right? 12 divided by root 3, we need to rationalize. We always want to look and see if this will in fact reduce. So 12 divided by 3 does in fact reduce, and that gets me 4 root 3, which is this side here. So remember, I still need to get the hypotenuse, and the hypotenuse is double this. This is half of the side of the original equilateral triangle. So if this side's 4 root 3, that makes my hypotenuse 8 root 3. So again, it's kind of all about knowing, are you going from a smaller side to a bigger side, or a bigger side to a smaller side? This is the smallest side in the entire triangle. So from here, I need to multiply to get there. From here, I need to multiply to get there. If I'm going from the bigger side to the smaller side, or the bigger side to the smaller side in that direction, I need to divide.